I'm Sabera. I'm a study manager at Test Labs, and today I'm being pressure tested. I'll be talking about material compatibility. So I'll go through some of these questions. What is material compatibility is the first question. So essentially material compatibility is describing how suitable a material is when it's put against different conditions and processes, and how those processes impact the material's chemical, physical and mechanical properties. Is material compatibility the same as biocompatibility? So this is a good question because it does sound like they are the same. Both names have compatibility in them, and they're both very important in terms of what medical device manufacturers need when they are assessing the safety and the functional performance of their devices. The difference is material compatibility is how processes that manufacturers will supply in their instructions for use impact the materials of the device when they put through those processes. Biocompatibility, on the other hand, is how materials can impact the human body when they've been put into contact. So it's more of a biological risk and a hazard to the patient rather than assessing what is happening to the materials themselves. When do I need to test material compatibility and why? So material compatibility, essentially you want to start the testing for that at the initial design phase of the product, because you need to understand which materials are suitable to use when producing this device. So it makes sense to have that involved in the initial design phase. However, manufacturers should also consider the long-term effects of their devices and what happens to the materials in that sense. So it should be a continuous assessment as well as an initial assessment. How do I choose materials for devices? So it is quite difficult to decide which types of materials will be suitable in the first instance because you don't have that initial data. But the things that we need to sort of consider when we are choosing a material for our device is essentially what processes will we put these instruments and these devices through. Is there sterilization processes involved? Is there cleaning processes involved? And how those sort of processes will impact the device will give us a good indication on which materials would be suitable. The other thing that manufacturers need to consider is transport and storage of the devices, because those are also environmental conditions that will affect the materials. So all these things are what we should be taking into account when we're selecting our materials. So part of that process of selecting your materials, you could start involving material compatibility testing in that stage of things. You could have samples of different materials and test them against certain processes just to give you some initial idea of what these materials are performing and how they're performing when we put them through these processes. What are the basic material compatibility testing? There's not really a basic material compatibility testing because it all depends on the specific use case of that device. Is it going to be, is it a material that's going to be sprayed on? Is it a material that's going to be immersed in a liquid? Or is it going through sterilization processes? All these types of exposure need to be considered when you're planning a method to test your material compatibility. So it all just depends on what type of exposure the device will encounter in real life. And then in the laboratory, we would simulate that use, whether that's wiping continuously, whether that's immersing the device for a specific amount of time, spraying the device, or actually putting it through cleaning processes, sterilization processes, and disinfection processes. We would involve all these processes in seeing how the materials are getting affected. Why is material compatibility often overlooked? So in my opinion, there are probably three things that factor into why it gets overlooked. I think the first one would be the rise in infection prevention and control practices that are happening more and more in healthcare ever since COVID. So because they're rapidly evolving, the chemicals and disinfectants that are being used are constantly changing. So manufacturers of medical devices, when they're selecting the materials, they may choose materials that they have previous data for, but they haven't really assessed how these materials are now are going to be affected with these new infection prevention and control measures. So this is why I think it has to be a continuous assessment, and material compatibility testing needs to be a long-term consideration. The second thing is probably a combination of cost and time. So material compatibility studies, as I said, it's better to do them as long-term studies. So manufacturers may not have the time to complete those studies in full, so they might get data that's not as representative as what they need. And then they may also choose cheaper materials that don't really meet the standards for any processes that are happening in healthcare. So cheaper materials are not as durable, so they're not really considering material compatibility in that sense when they're selecting the materials there. And the final thing is to do with regulatory guidance. There isn't as much sort of standard acceptance criteria set for material compatibility with medical devices. So manufacturers can end up choosing their own and selecting their own acceptance criteria, which might, again, not be representative of what actually happens in the real world. So they might not be, the data might not be as good as what it needs to be. What happens when materials degrade after sterilization? A few things can happen. Obviously, the sterilization processes often involve either extreme temperatures or the use of harsh chemicals like ethylene oxide or hydrogen peroxide. So when we consider the fact that we have these conditions, it's obviously going to impact the materials. And the way it can get impacted is they can obviously degrade them physically. If there's any cracks or crevices that start appearing, or if plastics become more brittle, then obviously that will have some impacts in terms of what residues are remaining on the devices. So these are all things that would happen could happen in a sterilization process if the material isn't compatible with that process. How early should compatibility testing start? So as I said, essentially you want to start your compatibility testing when you're at the initial design phase of your product. This will help you select the right materials that you need. And then you want to continuously test compatibility for long-term data and get some lifespan indications of the product. What is the biggest mistake in material selection? So I think the biggest mistake would probably be when you're choosing materials that are cheaper, essentially. So you want to have that cost saving, but that means that the material might not be as durable as what it needs to be. And these could lead to premature failing and then a reduced lifespan of the device. So it's important to not only go down the route of how can I save in terms of cost, but also make sure testing is done at that selection part of your journey when you're choosing your materials, so that you have some data to support why you're choosing those materials. What materials cause most surprises? So this is a good one because it's interesting to see how plastics behave when we do material compatibility testing. Normally, you would assume a lot of polymers have a lot of advantages to them in terms of properties. A lot of them are heat resistant. You can have polymers that are flexible, different polymers that are stronger in what they can do. But the surprise there is, even though they have those advantages, we do sometimes see that when they're exposed to certain chemicals, they do react, and then you do end up seeing the incompatibility when you're exposing those polymers to disinfectants. So I think that would, for me, would be one of the biggest surprises that we normally see. How do coatings complicate compatibility? So coatings are essentially what is put on over a material, and then it sort of protects the material surface underneath. The reason why it complicates material compatibility is if those coatings themselves aren't compatible, then they could start peeling or cracking and revealing what material is underneath, and then that material then becomes vulnerable to damage as well. The other thing to consider with coatings is what residues could it be leaving behind, what is leaching out if those materials aren't compatible. So in that sense, coatings could complicate testing. Is there a link between material compatibility and biocompatibility? So I think there is a big link, because when you are doing material compatibility testing, you're essentially testing how those materials perform when they are put through processes, and are they degrading. The reason why this is important for biocompatibility is if those materials are degrading, they are leaving behind cracks, they are leaving behind residues, and this becomes a risk when you are doing biocompatibility analysis. If those residues are toxic, then you would increase your risks in the biocompatibility assessments that you do. As well as when there's cracks on the surfaces, we notice that residues are more likely to remain on the device within those cracks and crevices. So then when you go on to doing biocompatibility of those devices, it might not pass or give you the result that you're after. So there is a big link between them, and I think they both need to follow each other when the assessment is being carried out. What data do notified bodies expect when it comes to material compatibility? So when you're doing material compatibility testing, essentially you are obtaining data that would help support any lifespan claims that you're making for the device. So this will all be put in the report that gets presented to notified bodies. So the material compatibility data can be used to support the lifespan of the device. It can also be used to support the claims that manufacturers make in terms of the device safety and functionality. So if you can prove that through repeated reprocessing, material compatibility assessments have shown that the device still functions as it should, there's no changes to its mechanical properties, its physical properties, then all that data will be in the report that gets presented to notified bodies. So it's all included in the whole reporting process of a medical device manufacturer's journey to put it into market. How do packaging materials interact with devices? This is a good question because it's actually not something I had considered before, so it prompted me to think about this a bit. But it does make sense to include packaging materials when assessing device material compatibility, because when a device is packaged and then transported and then stored whilst in those packaging, we obviously need to make sure that that packaging isn't deteriorating as well. The other thing to consider is a lot of the times medical devices are packaged sterile. Now, if those packaging aren't compatible, the materials aren't compatible with the storage and the transport conditions that are being used, then it will compromise the sterility of the device if those packaging become damaged. So it's definitely quite important to consider packaging when looking into material compatibility. When should accelerated aging be considered? So accelerated aging is used to help medical device manufacturers estimate the lifespan of the device. Now, if the medical device manufacturer is wanting to speed up putting their device on the market, it's at that point that they should do accelerated aging tests, because it means that they can get the data quicker than real-time aging studies. So this accelerated aging testing should be done when medical device manufacturers want to fast-track getting their product onto the market. What is the most common failure you see? This one was an interesting one to think about as well, because the failures that I see, they're not necessarily failures in terms of what the medical device manufacturer might expect. So what I would say is the most common observation that I see on materials when they've put through material compatibility testing is we often see discoloration of the coating. We see a lot of residue marks being left behind, and although that might not have an impact on how the device performs and its functionality, it could impact the device safety if it then ends up impacting the biocompatibility of the device. So although it might not be considered a failure, it's definitely something that later on in the long term could end up resulting in a failure. What risks are underestimated in reusable medical devices? Keeping on brand, I guess, with this pressure tested, for me, it would be material compatibility, because essentially when medical device manufacturers want to put their product into market, they're usually focusing on validating the cleaning and the sterilization processes, but they often overlook how those processes are impacting the materials. This information is also important when they're assessing the overall safety of the device, especially for post-market surveillance. They definitely need to have that data to prove that throughout the lifespan of the device it's still working as it should. So for me, that is what the risk is when they overlook material compatibility. We have noticed that our device changes color upon cleaning. Would this be a problem? So it depends how, at what point you had started seeing this discoloration. If it's towards the end of the lifespan of the device, then it's probably not going to cause much of an issue because the device is going to be put out of use soon anyway. But, and then the other thing to consider is, has it affected the functionality of the device? If it hasn't, then it's probably not as big of a concern. The only thing that should be considered is whether the discoloration has then affected the biocompatibility. So it would be good to, once this color change has been noticed, moving into doing a biocompatibility assessment to see whether the device suddenly becomes cytotoxic, or whether this discoloration is because of chemicals staying on the device, which would become toxic if in contact with the human skin. This is the approach that I would take. I've heard of tensile strength, but I don't know what it is. Yeah, that's a good question. So tensile testing is essentially testing the mechanical properties of a material. So you are basically pulling materials apart and measuring the force that it takes to break or form any cracks on that material. And that force data gives you an indication of whether the material is weakening based on what the initial state was. This could lead to material incompatibility in the long term if the material is becoming softer and more brittle. How long does material compatibility studies take? So this very much depends on what the medical device manufacturer is claiming. If they want to do material compatibility testing to determine the lifespan and confirm the lifespan of the device, then this could go on for a few weeks, maybe even a couple of months, just to ensure that those repeated uses of the device and processes that it's going through are simulated in the lab. So we would continuously do these and then get the data before and after. So those are long-term studies. There are some studies that you could do that sort of fast-track some and give you an indication of results in the worst case. For example, immersing a device in the disinfectant for 14 days could be used to simulate what it would be exposed to over 2 years. So you can sort of accelerate these tests depending on how you expose the device to the chemical. How many samples do I need to provide for testing? So normally with our material compatibility testing, we get the data in triplicate. So we essentially have 3 materials that get put through, or 3 devices that get put through these processes or cleaning practices. And then we analyze them and get averages for the results that we get. The additional samples that we'd need would be used towards controls. So we normally have one sample that isn't put through any processes, and it's used to refer back to when we're doing visual assessments to make sure that we have a reference of what the initial state of the material was. So yeah, normally 4 samples, 3 to test and 1 to keep aside as an unexposed reference control is what we call it. We claim 1,000 cycle for the lifespan of our device. How long should we test for? So if it's 1,000 cycles, it's probably good to start off with getting some data at interim stages. So if you test after 50 cycles, see what the device looks like. And then if it looks good, then we continue and go about it in that way. We still want to make sure we have data as close as possible to that 1,000 reprocesses. But 1,000 reprocesses within a laboratory environment doesn't necessarily mean that it will take as long as what it would in the real world. We can normally fast track these by doing them one after another continuously, and that sort of speeds up getting the data that you need. But when it's something to that scale, we normally recommend doing interim checks and ensuring that you have the data after a specific number of cycles, just so that you can see whether it is starting to fail or whether it's still good to go on for the full 1,000. So this was Sabera, and I was pressure tested today. I spoke about material compatibility. I think the entire process was quite interesting because there's definitely questions that made me reflect and think on past studies that we've done, and how that can be used in future studies. So in that sense, I think it's quite useful. And yeah, I definitely think medical device manufacturers need to keep considering material compatibility and put that as an important testing method within their requirements, so that they have a full picture when they're presenting to notified bodies.